So this is the part where we talk about the Hecke operators. Okay, so first let me explain a bit about how to think about these Hecke operators geometrically. So suppose you have a Q group again, and we have the symmetric space D, and we have an arithmetic group. It's going to be acting on the symmetric space. And we pick an element in the rational points of G that has the property that both gamma and conjugate by gamma on the right are commensurable. So they both of those groups have to have finite index in their intersection. Then we can make this kind of diagram out of that. So I have the locally symmetric space on the bottom there, both sides of the bottom, and then I have a different locally symmetric space at the top coming from the intersection of these two. And so on the right, so I have two maps there. So first of all, there's an obvious map going from thing upstairs down to D divided by gamma, which is you have the intersection of those two. That's the map S, okay? But the map T is a little more interesting. So we have a projection map from the quotient by gamma prime to the quotient by the conjugate, and then we can left multiply by this element G. And that gives us diffeomorphism between the quotient by the conjugate and then the quotient by the original thing. And the commensurability, because of the finite index, it just means that both of these maps are finite to 1. So the correspondence like this, it's really a pair of maps from this big thing to this small thing, induces a map on cohomology, and this is the Hecke operator. So it's the composition. Basically, what you want to do, if you look back at this diagram, is you want to start with a class over here and pull it up to here and then push it back down to here using these two maps. So you can do that with S star because it's cohomology, so it's contravariant, so it's easy to go in the direction that you want. The map T star is not something that you normally have in cohomology because it's going the wrong way, but because we have this finite index case, we can make this work, okay? Because it's finite to 1. You could also, if you want to think about it in terms of group cohomology, it's the transfer map, or you could also construct it using Poincare duality. Go over to homology, and then you have a map going the way you want, and then you go back using duality. But in any case, we can make this operator that's a self map on the cohomology. Okay, so this operator only depends on the double coset, so whatever G looks like in its double coset, and by composing these, we get this whole algebra, this huge algebra of operators acting. Okay, and so in fact, this is where we're using something special about gamma being arithmetic. So if we go back to this other, go back here. So I said, yep.
Can I ask a quick question? Because this mention of this algebra is always really opaque to me. Do you mean like a free algebra on these symbols and that acts by this specific action, or do you mean the subalgebra of the endomorphism algebra of H star that is generated by these specific maps? What do you mean?
Well, so what I mean is the algebra, there are relations, okay, but it's sufficient for our purposes just to think about it in terms of its action as endomorphisms. Realize it there. So it's not the free algebra on these symbols. There are, we can know some relations that have to be true because we're going to be acting on the cohomology, and that's all we care about. So I didn't write them down. It's a polynomial. So it's depends on the setup, really, like what the algebra looks like. So I didn't want to get into the details with that. But in the cases that we're going to be looking at, they're going to be of like different operators for different primes P, and it's going to then let P. It's going to look like a polynomial algebra. So we can just think of it as we only care about what happens in the cohomology. So we can think about them as what operators do we get in the cohomologies, endomorphisms of the cohomology.
You can just take one operator at a time, basically, is what you're saying?
Yeah.
Okay, and then Graham had a question.
The group element little g, where does that lie? What's that taken from?
Okay, so that is, I was actually just about to say a little more about that. So that was, it comes from the rational points of the group, not necessarily in gamma. I mean, certainly gamma would be something that you could take your element g from, but it comes from the rational points of the group, and it comes from the commensurator. We want that both gamma and this conjugate are commensurable.
So if you give it from gamma, the action would be trivial, though, right?
It would not be very interesting. That's correct.
Or an isomorphism at least.
Yes.
Oh, it's pretty trivial.
Well, it depends on this double coset, and so if you take gamma, if you take g and gamma, then you just get the trivial double coset, just gamma. So but what I was going to say is that you know, a priori this makes sense for any discrete group sitting inside of there, but to get a big commensurator, to have a lot of little g where this is going to give you something, that's where you need that it's an arithmetic group. So in general, for example, if you take some non-arithmetic discrete group, you will not have a lot of these. But if you have an arithmetic group, then you have this giant algebra of operators. Okay. Maybe it's helpful to look at some examples to see what they look like. So in the classical case, when we have gamma naught of n, and we take a prime that doesn't divide n, we can take our g to be this matrix. So here's a matrix that's not in SL2Z, obviously, but it is in the commensurator of SL2Z. If I construct gamma prime, as I said before, that will be finite index in SL2Z, and so will also in the conjugate. And then we know from previous discussions that this H1 of the locally symmetric space has something to do with modular forms. And in this case, we're actually just getting the classical Hecke operator TP on the space of modular forms. So in this case, we have different operators for different p, not dividing in. We have an operator when p divides in, but it's not the operator TP. It's slightly different. But in any case, they all commute with each other. We have this enormous algebra of mutually commuting operators acting on the cohomology.
So in this case, g of q, the rational points, is that, should I think of that as SLQ?
No, it's going to be GL2Q. So I'm really, yeah.
And the curly E here is dependent on K, right?
Yes, that is so that was the local system on Y gamma, and it comes from the homogeneous polynomials in two variables of degree K minus 2.
And the second K is not related to the first K, right? In the second bullet point?
No, it is different.
Yeah.
And the second one is just some index.
Yeah. Okay.
Yeah. So what happens when you go to SLN? Well, we actually have more operators now. So we can take, you know, for different p, we have this collection of instead of the single diagonal matrix above, we take these diagonal matrices where k varies. So we have kp's there. I mean, I could have taken, I guess I'm being a little sloppy about GL versus SL. I could have taken a different G and I would get the same thing. But
you could multiply this. You could conjugate with something in the center, right? And it wouldn't change the conjugation action. So that doesn't really matter that much.
Right. Okay. Why do we care about these operators? Okay, so the point is that these operators are what detect the arithmetic nature of the cohomology. And I don't mean because it's an arithmetic group, I mean the connections to arithmetic geometry. These are revealed by the eigenvalues of these operators. And here's sort of the general scheme in which this happens. At least I'm writing down something precise for SLN over Q. Okay, so start with SLN over Q with our group gamma naught of n, which means that the bottom row is congruent to a bunch of zeros and a single star at the end mod n. And now I can take the absolute Galois group of Q, just take the limit over all finite Galois extensions of Q, and you get this large profinite group that contains all the information about all these finite extensions. And then I take a Galois representation. So there's some technical words there, but we can kind of ignore them if we like. I mean, if you just think about it, it's really, if you don't want to worry about the continuous and all this kind of stuff, you can just think about it as a representation of a finite extension. There's some finite extension of Q, and we have a representation of that finite group. And then for each, and also this unramified condition is somewhat technical, but there's some finite list of bad primes that we want to ignore for the discussion. Just leave it at that. So we have a distinguished conjugacy class inside this giant profinite group called the Frobenius. And it comes from, well, we know for a finite extension what the Frobenius is, at least for unramified prime. And we just pass to the limit here and look at the conjugacy class we get in the big thing. And because we have this representation, we can consider characteristic polynomial of it, okay? So it's not sort of the usual characteristic polynomial you see in linear algebra class, because we kind of have the operator over there on the variable. T in this case is not the Hecke operator, it's just some variable in a polynomial ring that we're using to write down the characteristic polynomial. But in any case, we have this, and this encodes a lot of information about what's happening at the prime L in this representation. And everything is, and it's reasonable to consider this because basically everything that I've written up there, I mean, well, at least a frob L, is not a unique element. It's only defined up to conjugacy. So to be able to get something that's invariant or meaningful, we have to write down something that's an invariant of the conjugacy class. And so the characteristic polynomial is a great thing to do for that. Okay, so here's some arithmetic geometric data. And we get this, for example, from classic case where you've probably seen something like this is where you take an elliptic curve. And you can take the cohomology elliptic curve, they tell cohomology, it has an action of the Frobenius, you get a Galois representation. Okay, on the cohomology side, we have for each prime L not dividing n, I guess I want to throw away the one for P as well, we have these Hecke operators that I mentioned before. And they commute with each other, so we can look for mutual eigenclasses. And here, if we have one, we can package the eigenvalues of those operators together in a polynomial. It's kind of a random looking polynomial. It has some powers of L. It has the eigenvalues, has some signs. It's not that, at this level of discussion, it's not that important where it comes from. Essentially, if you want to know, it's like the local factor for an L function. So if you take n equals 2 and look at that case, this polynomial, if you replace t by L to the minus s, you're actually getting the local factor for the L function. For,
Can you be a little bit more precise by saying what commutes with each other? Just, I mean, so just the matrices for any L or for one fixed L and any K?
Yeah, this particular, I mean, this is we choose some prime L, and then we make this polynomial. So we want the prime to be not in our finite set. So I said not dividing in, but I certainly want the ones away from P as well. And for that prime L, I have that list of n-1 operators. And I can produce a polynomial attached to that prime L by this construction, using the eigenvalues of those operators. And there's no reason that I wrote ALK instead of TK, instead of AKL. That was just silliness. I should have written it the other way. So, and I'm claiming that, so this is really secretly, there's an L function here. After all, cohomology is related to automorphic forms, and there are L functions related to automorphic forms. And this is essentially one of the local factors that you're going to use to build an L function. An L function is defined by an Euler product over primes, and this is what that local factor looks like outside this set of bad primes. if I replace capital T, I mean, the L function has a complex variable in it. If I have to get that in there, so what I do is I replace T by L to the minus S, where S is my complex variable. So this is a polynomial, looks kind of random, but this is in some sense the right way to package these eigenvalues together to try to compare them to arithmetic information. Okay, if you accept that, then here's how these Hecke eigenvalues are related to Gauss representations. So first of all, the Hecke this polynomial that I wrote here lives in C of t, whereas this polynomial that I wrote down there lives in QP, well, those live in QP bar of t, okay, depending on what this looks like. So here, I have to compare them. I have to first choose some isomorphism between QP bar and the complex numbers. Just fix it so I can consider some place where these polynomials live in the same place. And then their amazing theorem, conjecture for many, many years, and was relatively recently proved, sort of simultaneously by Schulze and by Harris, Land, Taylor, and Thorne, that if you have an eigenclass in the cohomology, then there is a Gauss representation where the characteristic polynomial of that Gauss representation matches this Hecke eigenvalue. So when these Hecke eigenvalues are exactly reproducing this characteristic polynomial of the Frobenius. And this was proved simultaneously by these people overseas. And in fact, Schulze proved quite a bit more. He proved that it's even true for integral cohomology classes in the locally symmetric space, or even torsion classes with finite coefficients. Okay, so these were like major achievements in this story, because one of the biggest obstructions to proving this was that there's no, we can compute, we have Hecke eigenvalues because we have these locally symmetric spaces, and we have the operators acting on them. So we certainly can make sense of the left-hand side, but to try to connect it to the right-hand side, you have to somehow come up with a Gauss representation. And the classical case of the modular curve, we can do this because the modular curve is an algebraic variety. So we have its étale cohomology, which has an action of the Galois group on it. But for these locally symmetric spaces, in general, they're not algebraic varieties. There's no sort of natural way that the Galois group is going to act on anything there. And we don't have a setting where we have both operators acting at the same time. So we can't there's not really any reason for why they should give the same answer, except that they do. So this was a really major achievement. Okay, so when we're computing these eigenvalues, we're really computing very inaccessible arithmetic information. This is really, and a lot of times it's very hard to get your hands on this arithmetic information. This is the only way to do it, really, in some sense. Okay, all right, so now I want to talk about how you, yep.
Sorry, can you say a little bit more where the interesting information starts? Like it probably doesn't start for n equals 2, right? Or
for n equals 2,
and
for trivial coefficients, the interesting information is coming from, you take an elliptic curve and you have the étale cohomology elliptic curve, and you have the Galois group acting there. And classically, the way that we think about this, like if I go back to this other Hecke polynomial, in this case, there's only sort of one interesting eigenvalue there, which is when k is equal to 1. And in that case, what that number is recording is essentially counting points mod p on that elliptic curve. So if you have elliptic curve defined over Q, then for finitely many primes, you can reduce it mod p, and then you have an elliptic curve defined over FP, and you can count the points on that. And that is a very subtle arithmetic geometric invariant of that elliptic curve, how that varies with P. And these Hecke eigenvalues are exactly telling you that. They don't exactly tell you that number. What they tell you is P plus 1 minus that number. So they're essentially the same number. But that's where in that classical case where it comes from. But again, the reason that they were able to prove results like that for SL2 and not for SLN in general is that elliptic curve is an algebraic variety. The Galois group acts on its atal cohomology. So you have some place where both of these actions make sense.
Thank you.
Okay. Okay, so I want to talk about how to compute them. Now there are a lot of ways to compute these, and I'm only going to be talking about one technique here, but it would be remiss not to at least mention other techniques. I mean, they're extremely important and they provide totally different ways, or in some cases not totally different, but very closely related, but they provide different ways to approach these computations, and they all have their advantages and disadvantages, but let's just go through them quickly. I mean, we have techniques using the Jacquet-Langlands correspondence. So this gives a connection between Hecke eigenvalues on two different locally symmetric spaces, one of which is much easier to compute with because it's just a set of points. And so you can transfer information from one to the other under some circumstances, and that allows you to do computation. So this, for example, is used, it's the method of choice for computing with, say, Hilbert modular forms. And you can find software in various places to use that. There's also trace formula methods. This is really, I mean, it's an industry in and of itself, and in some sense, it's better for proving things than actually explicitly computing things. But there are examples where you can actually explicitly compute with it, and you get concrete answers out of it. And so again, I mean, the case I know the best is for modular forms for SL2Z, but I haven't really taken a dive in the literature to see how concrete and explicit other results are. But at least in that case, if you look in Lang's book on modular forms, a nice appendix by Don Zagier explaining how to do that. There are methods using theta series and Q expansions that are very powerful and totally different. So I'm thinking of, for example, for the symplectic group, there are work by Poor and Yuan using theta series to compute Hecke eigenvalues there. And in fact, even for non-cohomological symplectic, non-cohomological Siegel modular forms. So in other words, there's kind of like the analogs for SP4 of the weight 1 modular form. So those kind of things are completely inaccessible by cohomology if you're working directly with the symplectic group. But you can use other techniques. Q expansions is also another technique implemented in GP Paris just for working with classical modular forms. It works incredibly well. It's a great way to compute, and makes it very useful for doing experiments with classical modular forms. And there are other topological methods that I'm just not going to mention at all, but some of them are more closely related to the things that I'm going to talk about. Other ones are relatively distant from that. But in any case, this is not the only game in town. There are other tools in the toolbox that you can use to compute Hecke operators. Okay, so we're going to want to try to use Voronoi. We have our Voronoi complex and Kocher complex for over number fields, and we want to try to use that to compute cohomology with in various ways. So we naturally want to use that to compute Hecke operators. But there's a big problem that you face immediately when you want to do that, and that is that the Hecke operators do not act on those cell complexes. If they acted by moving cells around in some reasonable way, then we would be able to write down the action. But they don't preserve the cells. If you think about things in terms of the locally symmetric space and what those cells look like when you draw them on the locally symmetric space, you realize immediately that they will not be preserved by these operators. So here's a simple example to show that. So we're going to take the operator T2 on SL2Z, and I want to compute something with it and see an example of this problem. So I said that the operator depends on this double coset of, there was that matrix, the diagonal matrix 1, 2 for the operator T2. And there's a double coset, which is the double coset of that matrix inside whatever my gamma naught of n is that I'm working with here. So the way that you practically compute that is you decompose that double coset as a disjoint union of single cosets. And here I'm indicating those single coset, those representatives of single cosets by the set omega. So this is the representatives that you use to compute the action. Okay, so I mean it's an exercise in algebra to write out that that's what you need, and you can see details of this in many places. For example, Shimura's book on automorphic forms. There are a lot of places to write down to see this kind of stuff. But in any case, here's this example for this operator. There are 3 of them. In general, for TP, there's going to be P plus 1. But my action is going to be to take a cell, for example, the cell that goes from 0 to I infinity in the Voronoi tessellation, and then multiply that cell, just translate that geodesic over by using these matrices. Okay, you can think about it as doing fractional linear transformations on the upper half plane, or multiplying the integral vectors that give you a cusp by these matrices. But in any case, that's what you do. And what you find is that 2 of those Hecke images are okay. So they're green because green is good. Those are the first 2. If you take that geodesic and then you apply that matrix by fractional linear transformation to it, you will actually take that geodesic back to itself. It doesn't fix it point-wise, of course, it kind of stretches it in various ways, but it does take the geodesic back to itself. These first two guys here. That's the green one. But this last one doesn't do that. The last one takes that geodesic, which is originally running like this, and it brings it over to here. So here, down here, we have, I hope you can see the mouse. I can see it, so I assume that means you can see it. But you have the 1/2 down here, and then you have going up to infinity there, okay? So that red class is no longer in the cell complex. So we can't, if we only have the cell complex to work with, we can't write down what this thing is, literally, in terms of those guys. I mean, at least not sort of right away. However, it's easy to fix that. I mean, if you look at the upper half plane, you see that, well, clearly that red thing is homologous to the sum of these 2 orange things. And there's a triangle. It's not a triangle in the tessellation, but there's an ideal triangle in the upper half plane where the boundary is these 3 things. And so, and those 2 orange things are supported on the tessellation. So if I can find this, it's easy to see it here because I have this picture. I can just draw this picture, write down what I'm supposed to do. But at least it gives us hope that there's possibility to fix this in general. We have to be able to write down homologies like this to be able to rewrite our Hecke images in terms of data coming from the cell complexes. Okay. Let me explain a little more about that. I mean, so there's just one picture there, and this is a classical subject, so-called modular symbols and the modular symbol algorithm that definitely, if you've never seen it before, you certainly need to see it to be able to think more about what's going to come. And even if you have seen it before, it's maybe useful to think about it this way just for a little bit so you can make it a little easier to digest the stuff that's coming. So here's what it looks like in this case. So we start with we have our group inside SL2Z, and we have our locally symmetric space Y gamma, which is our open modular curve. And then we compactify it by adding the cusps to make this Satake compactification X gamma. And now we have the cusps, or the boundary. I'm going to write it as the boundary of X gamma. That's the cusps. So given 2 cusps now think about in the upper half plane, if you take the geodesic running from alpha to beta, Okay, and this is now in the upper half plane. And then you pass that geodesic down by taking the quotient. You're going to get something that lives on the curve x gamma on this topological surface. And because you started at 2 cusps in the upper half plane, that geodesic, when you push it down, is going to give you a geodesic that winds around this surface x gamma, but it starts and stops at a cusp. It may not be the same cusp, that's okay. It starts in one cusp and ends in a potentially different one. But in any case, it determines a relative class. It determines a class in relative homology, H1, of that topological surface relative to these cusps. Okay, you get a class that way. Well, that kind of class is called a modular symbol. And modular because modular curve, and symbol because we use symbols in mathematics to denote things, I guess. But that's what it is. And if there are some special ones inside there, which come from the edges of the tessellation, okay? Go back to this other picture. So we have an example of a modular symbol. It's going to be like this red thing. It goes from the cusp 1/2 to the cusp infinity. And then when we pass down to some quotient, we get something that winds around that quotient. But it's not unimodular. All the gray things and the 2 orange things are what we call the unimodular ones, okay? And why are they called unimodular? Well, because when you write those cusps as primitive integral vectors in the usual way, take a rational number, write it as least terms, you get a 2x2 matrix, and that 2x2 matrix will have determinant plus or minus 1. I mean, it's not really well defined as a determinant because I could replace those columns by their negatives, but at least if it's clear that what we mean here, that really, if you take the absolute value, you're always going to get 1. The modular symbols span the homology because already we see that the unimodular ones do, since they give us this tessellation that we can use as a cell complex to compute this homology group, okay? So now the great thing about these modular symbols is that the Hecke operators act on them. Okay, what we do is we just multiply the cusps by the coset representatives, just like we did in this picture way over here. We take a given modular symbol, in this case, the one corresponding to the going from 0 to infinity, and we multiply that, multiply its cusps by these matrices that give us the representatives for the double coset, and they move those cycles around and give us new cycles and therefore give us new symbols. Oops. Okay. So now we have a large collection of homology classes where we know that the Hecke operators act on it. And moreover, there's an algorithm, an explicit algorithm using continued fractions that allows you to write any modular symbol as a sum in homology of unimodular ones. So that gives a way to compute the Hecke action. You start with the unimodular ones, and you can use, those are in the cell complex, and we could write down a basis after we've done our homology computation. Take any one of those things in the basis, act on it by a Hecke operator, and you get some sum of these other things. Then use this algorithm to push it back to give you something supported on the original cell complex, something written in terms of unimodular symbols. Where do continued fractions come in? Well, let me show you an example. So I didn't draw this guy inside the upper half planes. You have to kind of imagine it, but it's going to go from the cusp 0 to the cusp 12/5. That is certainly not unimodular. I mean, so I've written it in this funny way just to emphasize the vectors that also encode the cusp. So the vectors here are column vector 0, 1, and then the column vector 12, 5. And clearly that matrix doesn't have determinant plus or minus 1. So this is not unimodular. But we can use continued fraction expansion of 12/5 to produce a list of unimodular symbols for our homology. And here's how it works. You just write down the classical simple continued fraction, and then you write down its convergence. And so what this means is you just truncate the continued fraction at some point. So we truncate it 2. We ignore the rest there, the first 2, this guy. Then we truncate by taking the first 2 2s and we ignore this last one. If we do that, we get the number 5 halves. And then if we take all of them, the final convergent, we get the full number 12/5. And then we just write down the standard list of unimodular symbols using those convergents. Okay, so the first two just involve the cusp at infinity just to get us off the ground. But then after that, we plug this is always what happens here. And then we plug in these convergents in pairs like this, and we've made a bunch of unimodular symbols. Okay, and it's clear that geometrically that this is the homology. I mean, why is it? Well, it'd be nice if I had taken the time to draw a picture, but unfortunately I didn't. So this guy is going from 0 to 12 over 5, and you can see that this is just running along cusps, along edges in the tessellation, making its way over from 0 to 12 over 5. Now, if you draw the picture yourself, you'll immediately believe that what I'm saying is true. But this works. And the real reason that it works, if you go back to your elementary number theory class, is that when you write down these convergents, there's this part of the theory of simple continued fractions is that when you write down these matrices that are unimodular that are built out of the pairs of them. It's one of the simple things you prove when you study these things. Now, in general, what do I do if I don't have one that starts at 0 and goes to some rational number? Well, I just apply an element of SL2Z to move one of those cusps to 0, and then the other one will either go to infinity, in which case I don't have to worry about it, or else it goes to some rational number, and then I do this, and then translate back. Okay, so that's the classical way to do this, and it works incredibly well. And it works in a lot of other settings. It works, for example, over number fields. If you have a Euclidean number field, you can try to play the same game. And it's been used by many people, such as Cremona and some of the students to do computations, and lots of other people. So it's really, really a powerful technique. Okay, now we want to try to do something for higher rank groups like SLN, or even for these GLNs over these number fields. And we want to use our co-curve Voronoi complexes, and we need something to replace a continued fraction algorithm, because in general, for a general number field, we don't have the same kind of stuff that's lurking behind the continued fraction algorithm to make it work. I mean, it may not be Euclidean, for example. It may have class number bigger than 1. And we also want to handle other cohomology groups. So in this case of SL2 over Q, we're working with H upper 1, which is the VCD, because that's the most interesting group. That sees the cuspidal cohomology, and it's the only interesting group in this case. But for other examples, we need to get below the VCD. We need to see some other groups, otherwise we'll be outside the cuspidal range, okay? And so we're gonna sort of enlarge, do something more elaborate than modular symbols, but it's gonna include that as a special case. We're gonna make a new complex on which the Hecke operators act, and it's called the Charbly complex, which was named by Lee Rudolph for Lee and Sharba, because they're really the ones who introduced this in their own work. Although, of course, Lee and Sharba did not call it the Charbly complex. And I think there was a real missed opportunity when it was named the Charbly complex, because I think it should have been spelled more like Sharba's name. I think that would have been, it would have been much nicer to actually spell it like Sharba and Lee instead of this kind of, I don't know, trademarked version of Charbly, so you avoid their proper names. But in any case, we're going to describe it for the rational numbers. And we'll have to leave the general number field case, or at least what we've done, as sort of undescribed explicitly. Okay, so here's what we do. So we make a complex in the following way. We're going to take tuples of vectors in Z that are non-zero, and we're going to index them in this way. So like when k equals 0, we have n of them. Then we just grow them as k increases, and we impose some relations on them. So they're going to be anti-symmetric with respect to permutations. If you permute them around, you pick up a sign, and we're going to consider 2 of them to be equivalent if one of these vectors is a multiple of each other rationally. So of course we could just work with, this means we could just work with primitive vectors if we want, but it's a little more convenient not to restrict ourselves that way. because of the way the Hecke operators work, but in any case, it's enough to do that. And we also just throw away the ones, we mod out by the ones if all of these vectors are contained in some hyperplane. So we want them to at least contain, they have to at least be a spanning set for Qn. So we take all the symbols like this, and Sk is the K-sharp, is that vector space generated by those symbols modulo those relations. And now we have a boundary map. So we just take the usual boundary map from algebraic topology class and apply it to each of these basis symbols. So that just means if we have a list of K plus N, we walk down the list, delete one at a time, and pick up a sign, and sum the result together. Okay, and it's a boundary map just for the same reason that it is in algebraic topology class. The square of it's going to be 0 for the same argument. Okay, so there's a complex. So this is called the Sharbley complex, and it's a homological complex, meaning the boundary maps make the degrees go down instead of like for a cohomological complex. And we have an action of SLNZ on this complex. We can just multiply each one of those. If given a matrix in SLNZ, we just multiply on the those various vectors, just on each one individually. And we also, of course, have any matrix. If we take any invertible matrix with integral entries, invertible over Q, we can also act, just multiply. And we have the theorem, in this case, by Borel-Serre duality, that the kth homology of the co-invariance of this complex, so this symbol, putting the little gamma there, means that we have to take this gamma action on the complex, and we mod out by all relations of the form u minus gamma times u. That the homology of the co-invariance is the same as the cohomology of the group with rational coefficients, as long as we keep our indices straight here. So going up in K goes down from the VCD.
Oh, you see, the Sharbley complex, that's a chain complex, is that right?
Yes,
So
that's
is
right.
it the chain complex of a simplicial set?
Yes, you could think of it that way.
Of a pair. Of a pair of simplicial complexes.
Of simplicial complexes or simplicial sets?
Simplicial complexes.
It's xi inverted from z, so they don't have to be.
Anyway,
Anyway,
we'll talk about it later.
Okay.
Okay,
Sorry about that.
Okay.
no, don't apologize.
Well, I talked to Graham in front of you.
That's fine. I'm in a different continent, so not offended. Actually, I wish I were there so that I could participate in the same way, but please do not hesitate from doing stuff like that. But don't say anything that makes me feel bad. Okay, so now the Hecke operators act on this complex because, I mean, there's a little work to see that that's true, but it's exactly the same action as what we were talking about for the modular symbols. If I take those coset representatives and I just multiply, I don't have any restriction on determinants or anything like that, so I have an action, okay? And in fact, the modular symbols, if you set n equals 2, are just exactly these zero Sharbleys. Those relations that I was implicitly using when I wrote down those homologies between all those cycles of different colors, those are the relations that I was writing down in that big list. That's what I'm using there. But the complex is not finite mod gamma. I mean, obviously, even if I look at the zero Sharbleys, those are just n by n matrices with integral entries where the determinant is not equal to 0. And that is certainly not a finite set modulo anything inside SLNZ because of the determinant. The determinant can be arbitrarily big. So we need something like the unimodular symbols. But I mean, we could use determinant, but I want to kind of stay away from that, at least, sort of a priori, because determinant is maybe not the right thing to do if you don't have a Euclidean field, or it's better to try to do something more geometric involving the complex itself. And that's going to be this notion of Voronoi reduced. Okay. Oops, now away. So let's say that a K Sharbley is Voronoi reduced if when you take these vectors that are defining it, those are integral vectors that are non-zero, we can make a rank 1 quadratic form out of them in this standard way, and then we get something living inside at the boundary of the cone of positive definite symmetric matrices. So quadratic forms. So if I want to say that something is Voronoi reduced if when I do that, all those points live in the same Voronoi cone. Okay. So in the case of SL2Z, that is the same as saying that it's just an edge in that tessellation. There's no other thing. But because the top dimensional Voronoi cones don't have to have every subset of them having determinant plus or minus 1, this is not the same thing as saying the determinant is that it's unimodular. It's a weakening of that. Okay. So if you take you have a complex there, a subcomplex of the Sharblies defined this way, and I'm just going to say geometrically it should be clear that this is computing the same thing, but I have never written out that it is, and I don't plan to write out what it is because I just generally we don't really care about this thing in general. We only cared about using it for relatively for certain degrees in the cohomology, for things relatively close to the VCD. And in those cases, the Voronoi tends to be simplicial in all these examples that we've worked with. So we don't have to really face this issue and try to figure this out. But I don't think, I mean, what would it take to prove this? You just have to write down sort of all possible Voronoi reduced things and think about all the relations and just throw them all in. It just seems very painful and maybe not worth the effort to do it. But I'm not saying that, I mean, it could be wrong. I'm not proving it, but I'm not disproving it either. I think it'd be nice if it's proved, but I'm not going to worry about it.
Well, what do you mean by that they all lie in the same Voronoi cone? So by Voronoi cone, you mean like the domain of a specific?
Yeah, so the Voronoi cones give you there's a collection of these top dimensional cones.
Okay.
They correspond to the perfect forms.
Okay, I see.
And you get a polyhedral decomposition, and it just means that they lie in one of those cones appearing as, it doesn't mean that they have to be in the, they have to span a top dimensional cone. They could lie in a proper face of it, but they can't cut across a cone.
I see. I was just confused because I think Martinet uses Voronoi cone for the cone of all.
Oh no, yes, that definitely. Well, then if that were the case, then this theorem would definitely be true. But I don't mean that. Certainly not. Okay. So in this example over here, the orange ones are Voronoi reduced because their vertices live in the Voronoi cone. They live in those unimodular edges. So, but the red one is not because its vertices live. There's no single Voronoi cone containing both of its vertices, which in this case, those Voronoi cones are the cones on these faces. This is a quotient of the quadratic forms by homotheties.
I guess that's one way to make a simplicial complex out of your Voronoi complex by just making everything into a
exactly. I mean, modulo this, not just hand waving, but like hand smacking that I'm doing in this statement. I mean, modulo actually proving that, yes. But what I would be saying is take all possible ways of subdividing the Voronoi into simplices without adding new vertices.
Yeah.
Now the problem with doing that, if gamma has torsion, is that gamma's not going to act on that. I mean, it will act, and then it will move those. You can't fix one of them. You have to take all of them. Then it acts. But then there are many obvious relations that have to be true. I mean, if you had a Voronoi cone that was a square and you divided it in two different ways by putting the two different diagonals in, a cone on a square, then you have to have a relation that says that the sum of two of them is equal to the sum of the other two. And you just have to, so you're making, but I think it's, at least in our case, we're not gonna, it doesn't matter, because when we get down at the very end, we're actually supported on the Voronoi and not just one of these potentially bad things. Oh, wow, I only have 10 minutes left. Okay, I guess I have to pick up the pace a bit here. Okay, so I'm just saying that we're gonna take a class and write it, it's given as a sum of Voronoi reduced things. It's a cycle mod gamma, and we apply the coset representatives, and then we reduce by some algorithm that I'm gonna explain. So let me just keep going past that. But I do want to use this slide because I'm proud of this boldface thing. So I think Google Translate says this means let the computer beware. And that is that these are algorithms, and then we're going to tell you what to do, but they're heuristic. We don't know that they're actually going to work. There's no proofs for almost all of these that they will ever take a Sharpley cycle and make it Voronoi reduced. And there are also some tweaks here and there that we're omitting for time. They're in the literature, but we don't have time to go into them. But these algorithms have never failed for any example, and they appear to be very robust. They appear, I really don't expect anything to go wrong. For example, we've done them for this complex cubic field. I don't expect anything to go wrong for any complex cubic field. This doesn't seem likely, but there's no proof. So, but we're not trying to prove anything. We're just trying to get data. So as long as we get data that's sensible, we're okay. All right. Let me explain what happens for the zero Sharpleys. So for the zero Sharpleys, and over the rational numbers and over Euclidean fields, we already know a way to make them unimodular. Like the actual notion of unimodular is what we want to use. We want to look at the determinant, and we want to make the determinant go down. And Ash-Rudolph proved a way to do this. But we're going to do something different in our case. So given a zero Sharpley, we want to find some point so that when we apply a relation by taking this one Sharpley built out of the original entries and this new point, then the resulting things are better. So they're closer to being Voronoi reduced. And I don't want to define what that means. I'm just going to leave it in quotes, but I'm going to tell you a way to find a point that's going to do that. And it's going to be different from this continued fraction type method. Okay, so we're going to use the geometry of the complex. So here, capital C is the cone of positive definite quadratic forms. So I'm going to take the column vectors in the zero Sharpley, and I take the cone generated by them over in the positive definite quadratic forms, meaning I take Q of the columns and look at the cone that they span over there. And then I take the barycenter of that cone. Now a cone is, here we've spanned it we have some specific spanning points that generate it, which are given by those xi's. So I just mean take the ray of generated by the sum of those things. So it's like a central point in the cone. Of course, if you vary the xi's, you can change what that point is. But if we take all the xi's to be primitive, then it's a distinguished ray inside the Voronoi cone. All right. And then here's the idea. There's a Voronoi cone in his polyhedral decomposition that contains that barycenter, some top dimensional cone. Usually could be a smaller dimensional cone, but there's some cone that contains that barycenter. Then I'm going to pick W from the spanning points of that cone. Okay. So I'm not saying anything about determinants. I'm not saying continued fractions. I'm just saying something geometric. I take my zero Sharpley, I realize it inside the cone of quadratic forms. I have a distinguished ray inside that resulting cone. And I use the Voronoi reduction theory to determine the top dimensional cone or proper cone face of such a thing that contains that. That's unique. It's uniquely determined. And then that Voronoi cone has some spanning points. I take W from that. Okay. And actually, this works. In fact, it works very well. It usually produces, if you go back and look at determinants, I mean, one measure of how these things could be getting better is by looking at their determinants. If you go back and look at those determinants, they usually are very small compared to the original thing. Okay, and in fact, it's really the reason it's working is somehow something to do with the negative curvature of the symmetric space, but I'm not proving anything about that. And this is just a heuristic, but the heuristic is that the negative curvature is what's making this work. Okay, so here's an example just for SL2. So the red one is bad. The barycenter, I didn't draw it in, but it's probably somewhere, let's say around here. And so I have this triangle that contains that barycenter, and I pick one of those cusps. Say I pick this one down here, and now these two orange ones that are in this relation are better than the red one. They're certain, if I compute their determinants, they've gone down and gone down substantially. They've gone down so much that it really looks like you're doing the continued fraction algorithm. Okay. Okay, let me talk now. This is we're getting close to the end, so I wish I had a little more time, but I'm going to go through this rather quickly. At least talk about what happens for one Sharpleys. So now we have a one Sharpley. We have a list of n+1 vectors instead of n. Okay, and now we can look at the submodular symbols, which is where we do the zero Sharpleys we get by deleting one of those points. There are n+1 of them. And we can ask whether or not those are Voronoi reduced. And so in practice, that means we compute their determinants and see if they're plus or minus 1 or 0. If they're some bigger determinant, we know we have some work to do. Okay, we want to make them better. But we want to try to reduce this thing only knowing that we can reduce its submodular symbols. We know how to make them better, and we want to somehow make it better. Okay, so what do? Well, we have n+1 faces. And we're going to assume for this discussion that all of those faces are bad. None of them are Voronoi reduced. They're all like off the tessellation. So we have n+1 of them, and for each one, we choose a reducing point using this method that we described before. Okay, so I'm just labeling them W1 up to Wn+1. And my convention is that the Wi is opposite the face that we obtain, the submodular symbol, by deleting xi from the list. Okay, and now one complication is that this boldface U is part of a cycle mod gamma. In the modular symbol case, we can do things on individual zero Sharpleys. But for one Sharpleys, they really are cycles mod gamma. We really have to remember the gamma action when we do this. So if I have an identification in, by gamma, when I pass to the co-invariance, that identifies faces of different one Sharpleys, I have to make sure that I'm choosing these points equivariantly. Okay. And now I have this original one Sharpley, and I have this list of these n+1 points, and I have to somehow produce a new one Sharpley cycle using these things. So, well, what do? Well, you use a hyperoctahedron. This is maybe not the most obvious answer, but I'll show you in a picture what's going on here. So this is the high dimensional version of the octahedron. You can think of it as just the convex hull in Rn+1 of the basis vectors and their negatives. Okay, and that's some polytope. It has simplicial faces, and I'm going to use those simplicial faces to write down a homology. And here's what I do. I take that polytope and I label EI with XI, and I label the negative EI with WI. And then I look at all the one Sharpleys that are labeled by the facets of O. Out of them, we have the original one, but we also have some other ones that mix X's and W's. And that tells me the homology. So let me just show you the picture on the next page of what this looks like when n equals 2. So in this case, the hyperoctahedron is just a regular good old-fashioned octahedron. And so I've labeled it as I described. And you can see that the triangles there correspond to various one Sharpleys built out of these X's and W's. If I take the boundary of that octahedron and think about what that is giving me in this complex, it's giving me that that face labeled by the X's is homologous to this sum of 7 things that you see on the other side. Okay, and that's just a standard computation of a boundary and of a chain. It's nothing interesting happening there. So out on the other side, you see that we've replaced some x's with w's. And we have various, so in the submodular symbols in this case are going to be the various pairs you get out of looking at those triples. Well, we have 3 of them that involve a single w and 2 x's, and then with the rest of them involve at least 2 w's. What happens is, because we have a cycle, the original list of x's was part of a cycle, some of those things on the right-hand side actually disappear. They do not really occur because they're canceled by the same things appearing in the boundaries of other 1-Sharblies in the original cycle. And those are the guys that have 1 W in them, okay? So these first 3, even though they're in the boundary of the octahedron, because this thing over here was part of a cycle mod gamma, and we chose these W's gamma equivariantly, these actually are not going to show up in the complex after we take the co-invariance. They're gone. But these 4 things are. They survive. And so I can think about it if I want as just I'm taking these 3 things here and I'm converting it to this list of 4 things here using these W's and X's. That's the effect of the subdivision, okay? And just very quickly, I'll just say that the amazing thing is that these are going to be better. These will not be better. The top 3 that disappeared are definitely not better because as part of their submodular symbols, they include pairs of x's that we know are bad, but they're gone now. There's no pairs of x's left in these. We just have pairs of w's and bigger and the original x's. And these are all better. And notice that it includes things like this list of w's. Those are reducing points chosen for the various edges over here. They're chosen independently. They don't have anything to do with each other. So there's absolutely no clear reason why this 1-Sharbly built out of w's would be better than the original one built out of x's, because we didn't try to do anything to pick the w's to make that happen. But in fact, this will almost always be unimodular over here. It'll almost always have determinants plus or minus 1 and 0 because of the negative curvature of the symmetric space. Because we chose those w's by looking at the Voronoi cones containing the barycenters of the edges, those will be very close together. Triangles in a negatively curved thing have, if you go down to their midpoints along those edges, those are close together. They can't be far apart. So in fact, usually these w's all live in the same top dimensional Voronoi cone, or at worst in things that are close by to each other. But the reason we can't prove anything is because we can't prove any of these statements that I'm saying about this will be better than this one. It's just that experimentally, it's always true. And it really has to do, I think what's really making it work is the negative curvature of the symmetric space. Now I'm 3 minutes over, so I'm gonna stop. But thank you for your attention and for asking those questions. I'm sorry that it had to be so fast at the end.
Well, that was our own fault, I guess.
But yeah, so we still have time for a question or 2 or comments if anybody has.
I would like to see these statements that you make here more concretely, and I wonder if you can, why you can't prove them. But yeah.
Yeah, I don't know why I can't prove them. So I have lists of them. I'm preparing, as I'm making these lectures, I'm preparing a LaTeX list of references. And they're spelled out very concretely in those. So I was going to make that available tomorrow after I finish the last lecture. But definitely it's written out very explicitly in the literature. And also the modifications as we pass to new cases, we encounter new phenomena and we have to adapt the method. And so the flat factors when the groups of units are big introduce new phenomena that had to be addressed, but there's no problem. So I think it's a very robust method.
I'll have a look at that for sure.
Okay, so if there are no further comments, questions, let's thank Paul again, and we'll start with Philippe. Is it a